This is a quick video to show you a little bit more about how Newton's method works. The simple prompt for this is that we're trying to find the cube root of 7. What number times itself will equal 7 when you multiply it by itself 3 times? So if we want to get exactly 7 with a cube root, we can write an expression like this, that x cubed minus 7 is our function that we're looking for the 0 for this. So I've got this, this is the blue function here. It's a cubic function, so it behaves sort of like what we'd expect. It's going up on the right. And our initial guess is like, well, suppose we're looking at 4 as our initial guess for Newton's method, and we create a line of tangency at that point when it's 4, comma, then 64 minus 7 would be 57. Then we would get this line, this approximating line, and we can say, well, what's the 0 of this line? That'll be a closer guess. And then I'm going to plug this in and then rinse and repeat and just keep getting closer. So if I drag the slider, that looks to me like it's about, that's 3 right there, so it's about 2.7. So if I drag this down to about 2.7, right about there, whoops, right about there maybe, then you'll see that my next approximation gets me much closer to the actual 0, which it makes sense that it's less than 2, because I know 2 times itself 3 times gives me 8, and I'm looking for what number multiplied by itself 3 times gives me 7. But I can just keep repeating this where it looks like that's slightly more than 2. So if I drag this down to be like 2.1, and then I get closer and closer and closer. Now the way we can use Newton's method to get very, very close is by pasting this value into my equation down here for A. But just to retreat a second, just to show you how this is used, here is Wolfram alpha, and I've asked Wolfram alpha, what is the cube root of 7? And you can see it's about 1.9129311182, so on and so forth. And if I want more digits, I can get more digits. It's thinking of more digits. So even though our calculators might max out, there are other ways to get more digits. Well, how does Wolfram alpha get more digits? It's basically doing the method that we are using here in Desmos, okay? So you can see if I wanted to get the first, I don't know, 8 digits, it goes 91, 29, then 31, then 18, okay? So let's just remember that. And then I go back to my Desmos, and I've got my guess is here that, well, let's just start it back somewhere bigger like this. And you'll see that my red dot down here is at the point of it being a 0, all right? So this is my B value. I copy this, and I'm going to paste this in to my guess at what A's value is. And I can just paste it in here, and you see it jumps. That's my new value, and my new approximation is now 2 and a bit. I can click on that and copy that, and I can just repeat this process over and over again, where now it jumps closer and closer. Now I'm below 2. I click on this, I paste it in down here, and I'm going to very rapidly zero in on this. Let's look at those first digits. Copy that, 1.91458, and we know that we're getting closer, and I'll keep copying this, copy it, and I'll keep coming down here and pasting it. And when we don't see any change in our digits, we know we'll have it. So we're 91, 29, 32, not quite there. Copying it in, pasting it in. And this is what, pasting it in. Okay, I think we're there, almost. Copy one more time, paste it in one more time. And there it is. There's no change. I've got 91, 29, 31, 18, 277. This is what Wolfram alpha is doing. This is what Newton's method allows us to do. Look at the formula down here. This is just the point slope version based on us finding the derivative of f and then saying, well, if I know the slope of my tangent line, my initial guess is this point A. Then this is the derivative at that point A, that's the slope, and then this is just my y value at A. So think through what this function means, and then you can see that I've just plotted those points. That's Newton's method. Thanks, everybody.